morning, everybody. Welcome to today's North Pacific Landscape Conservation Cooperative Science Management webinar, Stream Temperature Database and High-Resolution NorWeST Climate Scenarios. We're going to globally mute everyone's phone right now, and then Dan, you'll need to press star 6 to unmute yourself. I'm Mary Mahaffey, the Science Coordinator for the North Pacific LCC. And this project was initially funded by the Great Northern LCC in their geography east of the North Pacific LCC starting in 2011. And in 2013, the North Pacific LCC provided funding to the U.S. Forest Service to expand this project to include the remaining portions of Washington, Oregon, and Northern California. This project was selected because of the importance of this effort throughout the Northwest and beyond. I would like to introduce today's speaker and project lead, Dr. Dan Isaac. Dan is a research fisheries scientist with the Forest Service Aquatic Sciences Lab in Boise, Idaho, and his research focuses on understanding the effects of climate change, environmental gradients, and natural disturbance on stream habitats and fish communities, monitoring and modeling of stream temperature and species distributions, development and application of spatial statistical models for data on stream networks, and use of digital and social media to connect people, information, and landscapes. So thank you, everyone, for joining us today. And we'll have a question and answer period after Dan provides his presentation, so please hold your questions. And if you have questions or problems during the presentation, please use the chat box and send a message directly to NPLCC staff. And we will, at the end of the presentation, you'll need to press star 6 to unmute your phone in order to ask questions. So at this time, I would like to welcome Dan.
Well, thanks so much, Mary, and thanks, Megan, for setting this up. It's nice to have a chance to visit with folks about this particular project that the North Pacific and Great Northern have been supporting now for several years. And Mary and I talked a little bit about the timing of doing this webinar at the stream temperature workshop that was in Portland last November, and thought that here towards the end of January would be a good time because we were at the time thinking we would have finished the Oregon coast and Washington coast areas within the North Pacific LCC, and so this would be a good time to kind of give a status update and talk a little bit about what it would take maybe to do something similar in the northern half of the North Pacific LCC as we finish the southern half down in California later this year. So before I get going then, I want to make sure I acknowledge the various people and agencies that are critical to accomplishing what it is that NorWeST is doing. There's a lot of people on the technical team, 15 or 16 people that are involved, half of which are scientists that acted in kind of a supervisory role and guide the project. But then these folks that are not the scientists, they're actually probably more important to this project in terms of actually making it work and creating the information that's useful for a variety of things. And so these are the folks that are organizing and cleaning data from dozens of different agencies, people that are pulling it together into a big relational database so it can be used for something. Our GIS spatial analysts and web design people that then allow us to package that information in a format and put it on a website where people can have access to it. And so they're really the heroes here in terms of the advantages and utility of what this particular project is providing. 4 or 5 different federal and private organizations involved here: Forest Service, Trout Unlimited, CSIRO, NOAA, and USGS are where those folks come from. Okay, so just a brief outline then on what I want to try to cover today, and I apologize to folks that have probably seen similar presentations in the past. I've given lots of different versions of this talk over the last several years as the project has progressed, but some of the folks on the phone today will be somewhat new to it, so I still did want to go through some of the background in terms of motivation for the project, how we're fitting the model to these big temperature data sets and creating scenarios. But then towards the latter half of the talk, points 3 and 4 then, that'll be somewhat newer stuff, and I want to start focusing then on how the stream temperature scenarios are actually being used, because the information has been around now long enough that people are picking it up and using it for a variety of purposes, and that the great hope going into this is that we could make good enough stream temperature information and scenarios that then it can be used as a variable in lots of biological models and for a variety of monitoring purposes. And then lastly, talk a little bit about the future expansion potentially of NorWeST. There's interest now that we've done most of the northwestern U.S. in possibly extending the project through the southern Rockies and California, which would be just awesome if it were to happen, to think that we could maybe someday have one giant integrated consistent set of scenarios across the whole western U.S. That's certainly something that was beyond the scope of anything that I or anyone else was dreaming at the time that this project started. But then there's also interest in doing things like NorWeST north of the international border through Canada and Alaska. And that's equally possible, but there are some additional geotechnical challenges with working further north that don't exist in the lower 40 that I also wanted to address. Okay, so just as quick background, climate, when we think about what exactly constitutes that in streams, two basic things are varying through time at a point on that stream network. Its temperature and its flow, and of those, you could argue that temperature in terms of just setting that thermal regime, especially since we're ectotherms, is really an important master variable for many of the things that live in streams. And so that's kind of been the impetus for in places that have them setting total maximum daily loads and regulatory standards about what temperature criteria could or should be for different species and different life stages of species in different bodies of water. And so it's a little bit disconcerting then when we look at places where we've got good long-term trend monitoring data sets, and we can see that there's a slope to some of the relationships over time in those sorts of data sets, and in general we can see that things are warming up as climate change has been progressing over the last several decades. These are just pulled off of some of the larger river systems across the Northwest U.S. And when we do the attribution of that to try to better understand, what is it that's driving and causing those warming temperatures over time, there are two things basically on a network that change across years, and that's the interannual variability in air temperature and then the interannual variability in discharge. And so you can build little models that just look at the relative effects of those things and ask questions about what's most important in causing that interannual variability, and then associate that with the long-term trends at a site. And when we do that, and we published a paper on this a couple years ago, what we found is that stream temperature trends are closely tracking the air temperature trends at local weather stations. But the relationship isn't a one-to-one sort of thing. So for every degree Celsius increase in air temperatures at weather stations, we're not necessarily seeing a 1 degree Celsius increase in stream temperatures. Instead, streams and rivers appear to be warming at a slightly slower rate than that, somewhere around 60% as fast as air temperatures are increasing. And so that particular graph is just broken out by different seasons of the year over a 30 or so year period. The warmest trends or the fastest rates of increase that we can see seem to be occurring during the summer period, somewhat slower than during other seasons of the year. And when you look at some of those seasons, it's also interesting in that the ratio between the air temperature warming trends, stream trends, isn't necessarily as strong. One of the places you see that breakdown is during the winter period, and that's because a lot of streams, especially in the Rocky Mountains, are so cold in the winter they're flatlined on zero, and so increasing air temperatures aren't going to affect those systems until you get to the point where those streams aren't sitting at zero during the middle of winter. And then this was an interesting case looking at what was going on in the spring at long-term monitoring sites across the Northwest. At first, this was kind of confusing that we would see a trend in streams, but when we looked at then the air temperature trends at local weather stations over the same period of time, there had actually been a cooling trend there too. And so this was recently confirmed again by a paper by John Abadzuglu and Phil Mote that came out recently, that over the last 30 or so years, during the spring at least in the Northwest, there's been a cooling trend. And so streams very, very much do seem to be tracking what local climate, as related to air temperature trends, are telling those streams to do the warming or cooling. And then, so the Pacific Northwest is nice, at least over recent history, in that we've been kind of sitting in a climate bubble. We've got these strong climate cycles associated with PDO and ENSO, and over the last 10 or so years, for the most part, we've been in a cool phase of the PDO, which tends to make it a little wetter, a little bit cooler, and so we've seen some nice boosts in salmon returns and other things going on that are beneficial to fish. But for folks that track this closely, you'll note that the PDO anomaly about 13 or 14 months ago, and you can go see these on 1 and 8 Mantua's websites, but those flipped over to a positive anomaly. And so whether that's just a short-term thing or signifying that maybe we've flipped into a warmer phase is impossible to know, but at present at least, we're not as strongly into this cool phase as we have been recently. And so whenever it does flip back, and it will at some point, that then is just going to be enhanced by these long-term warming trends that we're seeing, globally. And in fact, despite the fact that we've been in a bubble in the Pacific Northwest recently, the climate is still cooking along on average across the globe. And 2014 just set a new record in terms of the overall average air temperature.
I don't know where he is, but we were going to...
Okay, so the Pacific Northwest then obviously has a lot on the line in terms of recreational, tribal fisheries, ESA-listed species, and things that are affecting land management planning across a really broad area, because many of these species, trout, salmon, and char, are cold water fishes, and so they're already sensitive to temperatures, and increasing temperatures then isn't necessarily going to be a good thing. The good news here, though, is that there are a lot of things that can be done to improve the quality of habitat and the resilience of these populations to climate change. The biggest question, as it's always been, is just prioritizing where on the landscape, given limited resources, you invest to do these sorts of things. And also then maybe as we start to think about climate change, is there a grand strategy amongst all these projects such that there starts to be synergy among them and they're not just kind of all off being done independently, but can they add up to something that's greater than the sum of the parts? In terms of thinking then about how you bring climate change into that sort of strategic planning for restoration projects in the terrestrial sphere, there's a wealth of climate models and scenarios to choose from. Literally, there are dozens of climate models that get run, and these are just examples of some of the more common ones pulled out of a graphic from one of Bill Mote's papers. But in the aquatic realm, we have nothing like that. In fact, when we started this project, there was nothing out there in terms of having a set of stream temperature scenarios. And so what's always been done in the past is that we'll use crude surrogates like elevation or air temperature to represent what might be going on with stream temperatures. But if you look at the correlation between those things, especially once you're into complex topography, there is a correlation there, but it's oftentimes pretty weak. So we have a tremendous amount of imprecision in using those sorts of things to do aquatic vulnerability assessments. And so the ultimate impetus for NorWeST was just to develop a set of regional stream temperature scenarios and to take climate into the water where fish actually live. And so what we've been doing essentially is working in the bottom left part of that flow chart and just building mesoscale models, river network models that allow us to predict stream temperature, and some earlier work that we did with Vic flows, predict those for all reaches within a river network, and then have those models linked to outputs from the global climate models and the regional climate models. So we can translate air temperature, precipitation into stream temperature and stream flow and make predictions at a reach scale that's more commensurate with the scale at which people are having to make decisions about where they're going to allocate their conservation resources and do habitat improvement work. So the nice thing about doing that in the Pacific Northwest then is that there is a huge amount of data out there to work with. And in fact, we knew there was a lot going into this project, but we didn't quite know that there was this much out there, and that's a lot of why it's taken us 4 years to get to where we are now. So far, at least, we've got more than 50 million hourly temperature records in this particular database now, more than 15,000 unique stream sites represented, and more than 80 different state, federal, private, municipal, county organizations have been gracious enough to share data with us. And so it's a tremendous resource now that's been pulled together, organized, and is put on the NorWeST website so that people have open access to the vast majority of these data. And just in terms of thinking about, if you wanted to start and collect that much data from scratch, what would it cost you to do? We're talking about something that's probably worth $10 million, just in terms of buying the sensors, hiring people, sending them to the field, pulling the data out of the field, organizing it. And so, for a small fraction of that cost, this project has basically organized what was out there into something that's more usable and accessible now to everyone within this region of the country. And so that cost, though, to collect the data is small in comparison to the value, hopefully, of the information that we can extract from that database. And that hopefully has a multiplier that's many times that $10 million, because if we can get good information on that database, it's going to allow us to invest more efficiently in terms of where we do restoration and where we try to conserve certain species on the landscape. So one of the challenges to then working with these big data sets, especially when they're kind of found and there's been no rhyme or reason to the way in which the monitoring or sampling has been done across all these different agencies, is that you can run into issues associated with autocorrelation, and so there's a certain amount of say redundancy among sites that have been measured close to one another. And when you fit a model to that, you have to account for that redundancy. Otherwise, you can end up with biased parameter estimates, and you get out predictions that aren't quite as good as they would otherwise be. And so on this particular project, we've been working with Aaron Peterson and Jay Verhoof, who have spent much of the last decade or so developing a new class of statistical model that is designed specifically for data that's been measured on stream networks. And so there are covariant structures that actually account for network topology and the way in which information flows on a stream network. And these just work much better with all types of data that are collected on stream networks. And they allow us then to account for that spatial autocorrelation, so we get unbiased information out of these big found databases. And they're kind of a perfect complementary tool to these sorts of big databases that we have in the Pacific Northwest with stream temperature data. Okay. And so next I'll just step through kind of some of the steps that we go through within one processing unit as we work our way through the region building these temperature scenarios. There's so much data in the Northwest that it's impossible really to fit one model to it and just be done with it. And so we kind of bite it off in chunks, the largest area we can handle, fit the model to that, create the scenarios for that, and then we move on to the next river basin to basically repeat the process. So here we'll just highlight what we did in the Mid-Columbla. In this particular landscape then, there were more than 9,000 summers of monitoring effort, almost 3,000 unique stream sites where people had collected at least one summer of data, and 19 or so summers during which people had collected data and that we pulled in data for fitting this particular model. Nice thing about that, because there are, in many cases, some data has been collected in different places now for almost 20 years. There's a lot of historical climatic variability that are represented in these temperature data sets. And so if we just look at the interannual variability in, say, air temperatures over that 20-year period, and the interannual variability in flows over that 20-year period, we've got a giant range of historical variability that we can work with. And in many cases, then, after we fit the model and represent an average historical baseline condition, and we think about making future projections, a lot of times we're not outside the range of what we've already observed in the historical record until we make a projection for the latter half of this century that we're in now. But we can still make future predictions out to mid-century and be within the range what we observed, and that gives us additional confidence then that the model is going to be accurate. We can predict what the future climate drivers are associated with the stream temperature scenarios that we're creating. Okay, so this set of graphs then just represents a contrast between sort of model performance we'd get out of fitting that Mid-Columbia database with kind of a standard set of non-spatial techniques. So the scatter plot in the upper right is just a multiple regression model that can be quickly done, say in Excel. Doesn't account for network topology, doesn't account for the redundancy in space of those measurements. And the scatter plot on the bottom right then is fitting that same data set using these new spatial network models. And so you can see you get a big performance gain. We can explain more than 90% of the variation in August mean temperatures and have an average prediction error of less than 1 degree centigrade. And so to make those predictions then, basically we're using a set of predictor variables there on the left. There are 11 of those that we use in each unit that we're working through. And these all come off of nationally available geospatial data layers. So one of the other things that allows us to do this project is that a lot of the pieces are already built that we don't then have to reinvent the wheel. And when we go into other parts of the country, say the Western United States or other parts of the lower 48, all these things have already been calculated by people that are experts in doing that sort of geospatial analysis. And all we're doing in the stream temperature model then is bringing together those predictor variables with a big temperature data set and with these new stream network models to basically make a map and some mathematical relationships that link all these things together. Okay, so of those variables then, the first 9 or so are spatial variables. Those are spatially fixed attributes of the landscape. The bottom variables then, discharge and air temperature, those allow us to account for the changes that occur between years and represent that interannual climate variability. And so there we use the discharge values that are measured at the USGS gauging stations within a river basin. And then we use air temperature anomalies that come out of Steve Hofstetler's Reg CM3 NCEP reanalysis because he's got all that stuff on a website and it's easy to pull down and use. And much more convenient than actually working off of the individual climate stations because he's already built an air temperature model that interpolates between all those air stations. And then one other thing just I wanted to mention because it's sometimes brought up, we've focused in the first iteration of NorWeST at least on modeling an August mean temperature, and that's for a variety of reasons, several of which are explained here. One, it's a lot easier to deal with a slightly longer term mean condition in terms of modeling it than it is a short-term maxima, even though a lot of those short-term maxima are what the regulatory standards are based on a lot of times. The challenge to modeling those, especially once you start linking it to a climate model, is that those maxima are occurring on a different day, a different week each year. And so you're really shooting at a moving target, and when you're trying then to link the outputs from a climate model to that, there's an order of magnitude more work in trying to figure out how to do that right than if you just focus on taking a monthly mean because that always occurs on the same date each year, and so you can create an integrated system by doing that. The other part of that then, and we don't lose very much in terms of the relevance for aquatic organisms, just because those August mean temperatures are so strongly correlated with all the other summer maximum metrics that are commonly used. And so if you just look at the strength of the bivariate correlations between an August mean and an MWMT or an MWAT or degree days, et cetera, they're all north of 0.9, it's somewhere around the average of 0.95. And so it's all basically the same information. We can call it whatever we want, but we're really dealing with the same information. And for that reason, then you can convert from one metric to another, fairly simply just by building a simple regression model to make that conversion between one and the other. Okay, so once we fit the model, then we get a set of parameter estimates. I mentioned before there were those 11 different predictor variables that we use. This graph is just representing in a standardized apples-to-apples way the relative importance of those predictor variables within that Mid-Columbia river basin. Bars that are blue are effects that have a cooling effect. Bars that are red have a warming effect. And then the hollow bars were predictor variables that didn't have a statistically significant effect within this particular river basin. And the spatial covariates then are on the left, and the temporal covariates that account for the interannual change are on the right. And so this is what it looks like in the Mid-Columbia. And then, as I mentioned before, each of these different river basins that we're modeling, we're basically using the same set of predictor variables each time. Rather than trying to go through a model selection process, and fitting the model over and over and over again, we just use logic at the front of this project to think about other things that people have found to be statistically significant in the past, and to think about the stream heat budget and how you would represent processes that affect the heating and cooling of streams on a river network and through a landscape, and basically just use those sets of variables and lock those into the model. And so what allows us to do then, that's kind of a nice and interesting thing from the perspective of stream temperatures, is we can make comparisons, or we can look across these different river basins to get a better sense of which drivers are always important and which drivers kind of come and go in terms of their relative importance in different landscapes. And when you look at these, then you think about the things that we're using in the model, things like elevation, stream slope, presence of lakes, latitude, base flow index, drainage area, et cetera, A lot of these things that we're using in the model are geomorphic attributes. So they're something that isn't really varying, and it's not something that we can have much of a management effect on. And yet, those things allow us to account for the vast majority of spatial and temporal variability in these temperature data sets. And so when we start thinking about management effects being layered on top of that geomorphic template, that variability and that effect that management has is real, but it's also relatively small. It's almost like an ant riding on the back of an elephant. But again, it's the thing that we can affect, so we do need to try to understand it. And the two places in our model where some of that management effect might be wrapped up then is in the riparian condition and then discharge, if there are local things that are affecting the amount of water that's being, say, taken out of a stream or added to a stream. And I'm not going to spend a lot of time on this, but I did just want to quickly highlight the way in which we're representing this riparian canopy variable in our model, because people are starting to ask this question about, well, how do we tease out, maybe management effects from the scenarios that you're creating? And so in our case, because all these variables have to be things that are already represented geospatially across broad areas so that we can pick those up and use those as predictors as we go into modeling different places, we're using the percent canopy variable from the 2001 National Land Use Cover Database. And we've tried different ways of looking at this, and we would always kind of compare it back to some places where we had some really good radiation estimates to kind of figure out what worked best before we made the decision to go forward with this. But this was the one that we found that is commonly available and works well in these temperature models. And so how we're representing a canopy effect is just by the percentage of pixels along a 1 kilometer stream network that are classified with that percent canopy rating, and that then goes into the model as a predictor. If you're in a place that has a really high canopy rating, then you've got more shade on the stream. If you're in a place with a really low canopy rating, presumably there's less shade on the stream. And so far, at least, this does seem to work in the model kind of the way we'd intended it to. it's always statistically significant, and it always has a negative effect on temperature. So the more canopy there is, the cooler the stream is at that particular place. We did do some modifications to it that I should mention. Because that 2001 NLCD layer was the most current at the time that we started building this model, and there'd been a lot of fires that had happened since then, we modified the values of those percent canopy variables within fire parameters to kind of bring those down to something that was more realistic. But other than that, we're basically working off of that National Land Use Cover database. And probably there's going to be a lot more on this particular discussion soon. I think Rochelle Labiosa with EPA is organizing a webinar in a few weeks to talk more specifically about this particular topic of teasing out management effects from these temperature models and seeing if there isn't a consistent sort of methodology that could be developed for doing that sort of thing. Okay, so once we've fit the models in and we've organized the database, at that point most of the hard work is over, and then you've just got a tool that you can use to create all sorts of different temperature scenarios, either historical reconstructions of conditions you've observed or future projections based on outputs from the climate models. And so basically, in our model, we just have to adjust the values that are associated with the air temperature parameter, the discharge parameter, or we could play around with the values that are associated with canopy values as well. So we're creating something like 20 different historical scenarios. We recreate each individual climate year starting in 1993, going through 2001, although now we're starting to also go through 2013 as we're building these scenarios in new places. And then we've also got a few composite scenarios where we just average across a 10 or 20 year period. And so those are all basically ways of trying to represent things that have already happened, and there's a lot more metadata that explains the details of all these scenarios on the project website. Once you can do that, then you should be able to recreate conditions, especially that have already occurred, fairly accurately if you've got a good model. And so this is just a time series stepping through the Clearwater River Basin in northern Idaho, what that historical year sequence would look like. So starting in 1993, this is the interpolated map then for that particular river network. And if you look at the upper right then, that's the predicted versus the observed for temperature sensors that were in the water that particular year. And if you look at the bottom right graph, then that just shows the interannual variability in air temperatures and discharge. And so I'll just quickly flip through this, and you'll see warm years, cold years, but the model, by and large, does pretty well across those different sorts of climate years. Usually it's predicting at least 90% of the variability at those sites where you've got temperature measurements, and then sometimes even more than that, 95, 96%. And it's doing so across warm years and cold years, high flow years and low flow years. So gives us a pretty good sense that we've got a model that works pretty well at this river network scale. Another way of thinking about this, especially as we start thinking about using these models to make projections into the future, is to look at the climate envelope that you've already observed and ask questions about, when we do make those projections for the future, how far are we going outside of that climate window? Are we extrapolating a long ways or not very far? And so here I've just plotted what the August discharge values look like over that 19-year period in the Clearwater Basin relative to the August air temperature values. And then that red dot represents the S1 baseline scenario, which is just the average across all of those climate years. And so we can then just look at what the model predicts if you're in a really warm, low flow year, and that would be that graph that's in the upper right. Then we can look at what the model would predict in a really cool, low flow year. And so again, the model does pretty well, very different climate space. Or we can look at what the model does in kind of an intermediate temperature year, but a really high discharge year. And again, it does very accurately. So it's performing well over this range of climatic variability. And the question then, as we think about the future, and where that climate envelope is going to go is it going to keep performing well? And so certainly through mid-century, when we're looking, say out to the 2040s, and we're talking about, a 2 or 3 degrees centigrade temperature increase, and during the summer at least, maybe a 10 or 20% reduction in summer flows. That's represented by that oval circle there. We're basically still on the edge of the climate envelope that we've already observed, and so I guess I'd be highly confident that the model is going to give us accurate results. When you get out to the 2080s, then you are extrapolating beyond the range of the variability that you've observed, but there's nothing you can really do about that with models like this. So the assumption is that unless the physics change really dramatically over that additional 2 degrees centigrade air temperature increase, the model should still perform fairly well. Haven't heard any logical reason, so far at least, for why it wouldn't still make accurate predictions going out further into that climate space. Okay, and so this is kind of where we are at present. As we organize the data, fit the model, create the scenarios, then we use those to make predictions throughout the full river network. And as I mentioned before, we had just finished the Washington coast a few weeks ago and sent out that information, and so that's kind of why we tried to time this webinar for when we did. And at present then, what we call the temperature blob has swallowed something like 46,000 summers of monitoring data and has created thermal ooze, high-resolution stream temperature information across more than 450,000 kilometers of stream in the Pacific Northwest. And so the other nice thing about this is that the model is very accurate over that huge amount of data and spatial network. We're accounting for more than 90% of the variation in August mean temperatures, average prediction error of about a degree centigrade, and we're making predictions at a 1 kilometer resolution along all streams within that regional river network. And so when we get done doing each state, kind of as we work our way through the process over the last 4 or so years, kind of a fun way of commemorating that and thanking the people in the state that have sent us data is just to make these state thermal maps. And so we sent one of those out for Washington several weeks ago as well, and people have responded really positively. They like that kind of end product wrapping up the information for their particular state. Okay, so future scenarios. So once we've got the baseline model fit and we can accurately represent historical conditions, then you've got a foundation built for making projections into the future. And in this case, then there's all kinds of future projections out there. When we started working on this project, the AR4 emission scenarios were the most recent. Since then, the CMEP5 stuff has come along, and there's not going to be a shortage of future projections anytime soon. And so, rather than trying to keep up with that game, and every time new future projections come out, us scrambling to make new stream temperature projections, we've just kind of pulled back and looked at all the things that are out there and realized that the biggest uncertainties about what's going to happen in the future aren't things that we can capture in the climate models, right? Most of that uncertainty for what's going on later in the century has to do with greenhouse gas emissions, which have yet to occur. And so rather than trying to represent every possible scenario, we're pretty happy just representing kind of a mid-century scenario when the climate models are pretty consistent, and then a higher-end scenario towards the end of the 2080s. And so that's going to bracket whatever happens in between then. And the big take-home, I think, with regards to all the futures is that they're all predicting things are going to get warmer. And so in terms of us adapting as fish biologists and other people that care about natural resources, that's the biggest thing that we have to do, is just realize it. Regardless of the scenarios we're looking at, it's just going to gradually get warmer. And so we need to think about how we adapt to that going forward. That said, we do have a suite of different future scenarios then that we've created, and they're also on the NorWeST website. There are about 10 of these. These are linked to the A1B warming scenario and the 10 GCM ensemble that SIG developed that best represented historical conditions several years ago. These are all tiered off of that. And so we've got the 2040s and we've got the 2080s. And then we've also got some scenarios that are, IPCC free, in that there's no assumption made about the timing of when things happen. They're basically just looking at what the historical scenario is and then adding 1 degree centigrade or 2 degrees centigrade or 3 degrees centigrade onto that. And so basically you can kind of pick and choose what it is that you're most interested in doing and the level of climate science that you want associated with the different future scenarios. The one thing that is, I guess, different or unique about the future scenarios that we've made and is different about the way stream temperatures respond to climate forcing than the way the climate responds to greenhouse gas forcing is that not all streams warm by the same amount when exposed to the same amount of climate forcing. And so there's different reasons for why that might occur. And we've explored that in this recent paper by Charlie Luce. And the biggest thing that we found there, or the take-home, and that we incorporated then into our climate scenarios, was just kind of this general pattern that we've seen of streams that are colder being less sensitive or less responsive to climate forcing. And so there's differential sensitivity in terms of how streams across that river network are going to change. And so we can and have incorporated that sort of differential sensitivity into a subset of our future scenarios. And so that is described then in the metadata for those scenarios that account for that. In terms of the magnitude of change then, once we look at that, the stream temperature response based on the SIG 10 GCM ensemble for the A1B trajectory, these are the different river basins that we've thus far completed. The red bars represent the average amount of stream temperature increase relative to a 1980s baseline within each of those river basins, and you can see that there's a decent amount of variation among those. Places like the upper Snake, which we're calling here the Snake Bear, don't seem to be nearly as responsive to climate forcing, and the thought there is that there's a lot of fractured basalt and a lot of groundwater in that particular part of the world, and so that just seems to buffer the streams there a little bit better than it does in other networks across the region. The black bars then represent the projections for the 2080s. And so if you just want an average number to think about, basically it's saying 1 degree centigrade stream temperature increase by mid-century, 2 degrees centigrade stream temperature increase by the end of the century. Also want to realize that 1980s baseline that we're working off of here, we're 30 years past that, and so we're kind of intermediate between that and the 2040 scenario. So you could maybe knock a little bit of a future temperature increase off of that because we've already experienced it. And the last thing then is again, those results are showing the average change across all streams within a river network, but within that river network, because we're accounting also for differential sensitivity, some streams are warming 50% faster than other streams within those river networks, and those we think are probably the most accurate climate scenarios that we're producing for the future period at least. Always good to kind of look back and ask, what's actually been happening. So if we don't want to think about the uncertainties associated with future projections, just knowing what's been happening and thinking about extrapolating that trend into the future is another way that future scenarios can be done. And so if we use the model then in kind of a hindcast mode and just reconstruct what the warming trends have been within each of these river basins, again, there's variability across those, but if you just want an average number to look at and think about the rate of stream temperature increase over the last 44 years has been about 1/10 of a degree centigrade per decade. So it doesn't sound like much, but you add that up over the course of half a century or a century, and that ends up being a fair amount of warming in streams. So when this stuff gets done, then it all goes on the NorWeST website. We're distributing series of different products there. The GIS shapefiles, which are just the interpolated maps, and they can be pulled into projects for a variety of planning purposes. And then raw data summaries. A nice thing about this project is that the vast majority of people that are sharing data with us are also willing to have it publicly put on the website so other people can benefit from use, and probably 90 or 95% of data that we've had sent to us then actually end up on the website. And then there's this nice interactive tool that through LCMAP we can port the information from the climate scenarios over to this, so you can actually go online and web surf the BLOB. You can click on any particular stream reach or data point within that stream thermalscape then and get information about where the data came from, what the historical prediction is, what the future predictions are at that particular site. And also then the hope is that, raw data, empirical data, that's the fuel that all models run on. And so just by making more data available, we're hoping that we can really accelerate the efforts of other researchers and other people that are interested in building temperature models, so that they can just go to the website, grab it, and use it, so we can create more information more rapidly about how streams are responding to climate change and what their overall thermal regimes are like. One thing to note is that at present, so far, we've only had time to organize the August stream temperature data and get that on the website, but we are getting really close to having non-August stream temperature data cleaned up and posted to the website. And so we'll go through a permissions process again for that, check back with people that sent us the data to make sure they're okay with us distributing it. But sometime in the next few months, we're going to start putting up non-August data. And two, then there's a lot of additional new full-year data that are being collected out there as well. And this graphic just shows places that are in the water, or sensors are in the water currently, collecting new full-year data sets. And so there's going to be a tremendous amount of additional information to work with going forward. I think I'll just skip past that because I want to really get to this last part of the talk and focus more on the ways in which now that this information, the NorWeST scenarios have been around for a while, how people are starting to pick that information up and actually use it for doing biological vulnerability assessments and building models that allow us to more accurately predict where some of these different critters occur in space. And so some of the benefits of the ways that we're seeing this information now being used, and maybe there are folks on the call today that during the discussion period could provide more details on some of this, because these are just kind of the general things that I've heard about. But with regards to temperature monitoring itself, I think just the fact that we've got one cross-agency organized database that people can go in and look and see where data do and don't exist is leading to a big increase in terms of the efficiency and a lack or a decrease in the redundancy of temperature monitoring now that's going on. People are spreading their samples more evenly across the landscape to fill in gaps, and in some places where a lot of data already exists, to just stop collecting data there for a variety of reasons, because there's not much more you can add once you've got a sufficient amount of temperature data. More people are collecting now full-year data as opposed to just summer-only data, because, again, we're realizing and seeing that that's been a gap in the database or the temperature monitoring efforts in the past. I know Oregon DEQ are thinking about ways of using the temperature models with some of their macroinvertebrate surveys to see if it doesn't allow them maybe to extrapolate some of those biological patterns beyond the places where they've collected temperature data in the past, to maybe make network scale inference about the condition of streams as reflected through macroinvertebrates. And there's a big discussion going on then about how TMDL standards might be revised to accommodate some of this information. In terms of how it's being used in salmon and resident fish research, Peter Wesley and Andy Dittman and Tom Quinn at University of Washington have a big hatchery stray rate database for the interior Columbia that they're using this temperature information with. It sounds like that there's a big interannual temperature signal in terms of that having an effect on the rate at which fish or adult fish that are returning to hatcheries stray. And during warm years, they think they're seeing a lot higher stray rates than during cool years. And the NorWeST scenarios basically gave them a standardized way of looking at that across all the hatcheries and across all the different years. Folks at the University of Idaho, Tracy Bowerman, Matt Kiefer, and Chris Caudill have also pulled together a big pre-spawning mortality database on Chinook salmon across the interior Columbia, and they're looking at those mortality rates relative to, again, the standardized predictions of temperature that NorWeST can provide. And then other folks are using the historical scenarios and maps as a predictor variable in species distribution models for different, a variety of different species. And then in terms of the ways it's being used in climate vulnerability assessments and land management planning, there's been a whole series of those, starting with the Blue Mountains Adaptation Partnership last spring, going into the Northern Rockies Adaptation Partnership over this recent fall period, wherein these temperature scenarios, when we now go in and start doing the fish vulnerability assessment piece, they're just kind of the foundational piece that we build all the fish distribution maps on top of, whether we're looking at trout or salmon or other species. Southwest Crown of the Continent Initiative in Northwest Montana is using the temperature model and the fish models that go with that in terms of how they prioritize landscape restoration. And then regional bull trout vulnerability assessments and cutthroat trout vulnerability assessments. Jason Dunham and other groups are working on that particular topic through a variety of projects. And again, these temperature models and the outputs go directly into doing those sorts of vulnerability assessments. And here then I'll just quickly highlight some of the ways that the folks at the University of Idaho have been using this information with their pre-spawn mortality assessment. And so they've pulled together survey data where they're going out to the spawning grounds and finding fish, Chinook, that have died prior to spawning. And then they're basically relating those mortality rates relative to a NorWeST temperature scenario map. And some of their preliminary results at least suggest that there is a pretty strong temperature signal there. Once you get into streams where that average August temperature is warmer than 20 degrees centigrade, they look like they just have a chronically high pre-spawn mortality rate. Probably not surprising, but then you think about the way you could use this information going forward proactively. You can start to highlight then that next set of streams that right now maybe haven't been showing very high pre-spawn mortality rates, and start to look at them more closely and see if there aren't things that can be done specifically on the ground to avoid that future bottleneck that we might be heading into, because all of these places now are spatially mapped back to a specific reach on that network, and you can look exactly at where those next critical places may start to occur in the future. In terms of developing thermal niche criteria and temperature standards for species, once you've got a good thermal template to reference your biological surveys against, then you just have to pull together those biological surveys, drop them on that temperature map, and you can pretty quickly start to make scientifically defensible, accurate, field-based predictions about what's too cold and what's optimal for these different species. We think this will be a generalizable approach, so we're talking about macroinvertebrates or amphibians. They're all ectotherms. They're all going to be regulated by temperature to a certain extent, and for some of the data sets that we've been working with now, basically you get all that stuff set up, you push the go button, and you can start to do this kind of in batch mode in a consistent manner for dozens of different species once you've got enough observations of where those different critters occur in the wild. And once you can do that, and then you make that a prediction about what's too cold, what's too warm, you can map that back then to specific places on the stream network. Here we're just looking at the Clearwater River Basin in northern Idaho for rainbow trout. Places or streams that are shown as blue here are too cold, red are too warm, black is kind of the optimal zone for this particular species. And under different climate scenarios then going forward, in that particular case for that particular species, climate change from a thermal perspective at least isn't going to be a big deal. But if we look at rainbow trout, or brown trout, with a very different thermal niche criteria, that same landscape, same set of climate scenarios, it's obviously going to be a really big deal. And then is by developing this set of scenarios that provide more specific information, we can go beyond where we have been in the past with relatively coarse regional models to much more precise landscape-level models that give us stream-specific and reach-specific predictions about climate, so that can feed into the scale at which people are making decisions on the landscape about where they're going to invest their limited resources. And lastly then, or here very much towards the end, that there is a community of users now that are forming around NorWeST. We have some ability to kind of track just the number of people that come to the website, and periodically then we can go in and make maps that just show where people are visiting the website from. That launched about 3 years ago. Since then, we've had 18,000 visits to the website. More than 1,000 different things have been downloaded from the website. People are using it predominantly in the Northwest, but we see a lot of interest from other parts of the country as well, and even globally. When you start to look at Europe, and you think about the similar issues they have there with temperatures becoming too warm for some of their species, or parts of Asia even, people are starting to tune into what's going on here in the Northwest and pay attention to it, and probably in some cases trying to figure out how to do something similar. So we're not talking about Amazon levels of traffic or Facebook levels of traffic, but we average 30 or 40 visits a day in terms of people coming to the website and getting information about stream temperatures. Where things are now currently, we've done the scenarios for the Northwest. We've done them also for the Lahontan Basin through some collaborative work with Trout Unlimited. We're in the process now of the east side and finishing the scenarios for central Montana and the state of Wyoming. And once that's done, probably in a few more months, then we'll flip back to the west side and figure or do the last part of the North Pacific that goes down into California. Here's just a pretty thermal map of what that stream thermalscape looks like across the western United States where it's so far completed. And in terms then of thinking about extending this to other of the country that may be interested in it, the foundational piece that we can build on top of is really just having a nationally consistent geospatial stream database. That we've been using is the NHDPlus Streams layer that has been jointly developed by EPA and USGS over the last decade or so. And the beauty of this stream layer is that it's got unique reach identifiers for every reach, but it's also got dozens and hundreds of predictor variable covariates that are linked to each of those reaches. And through, say, the National Fish Habitat Partnership, they've developed databases that bring in even more predictor variables for those individual reaches. And as I mentioned before, that's all done for the lower 48 states, and so expanding NorWeST to other parts of the country or doing similar things to NorWeST in other parts of the country, that's all relatively straightforward down here. The challenge that we run into when you think about trying to head further north and going into Canada or up in Alaska is that the NHDPlus layer doesn't yet exist in Alaska, though it's something that they're working towards having someday. And then Canada has kind of their own hydrology layer that probably would take a certain amount of tinkering to be able to do these sorts of things in British Columbia and Western Canada. And lastly, I just want to give a giant thank you to the folks in the Landscape Conservation Cooperative System, the North Pacific, Great Northern. They've just been awesome to work with. They had the vision to fund this and make it happen. And then especially want to thank hundreds of people from all these different agencies that have been willing to share data with us to make that database that we've compiled for NorWeST probably the biggest in the world. It's adding extra work to your already busy schedules when we ask you to pull your temperature data together and send us, but people have just been wonderful about doing that. And so just wanted to thank you. And also, lastly, just note that I think what's going on in the Northwest then with temperature is going to have a lasting effect, not just here, but other parts of the country. So some of the folks that run the Trout in the Classroom program with Trout Unlimited contacted us a few months ago, and they're interested now in actually starting to get some of these classrooms or include in their curricula temperature monitoring. And so given that they're in more than 4,000 classrooms across the country, you know, over the next few years, there might be thousands of additional streams and lakes where we're collecting temperature data, and hopefully we're going to influence a few of those kids towards being the next generation of stream climatologists. And that's all I've got.
Thank you, Dan, for your presentation. This is great information. And for everyone, we are recorded the webinar, and so it'll be available on our website. At this time, if you have questions, if you can unmute your phone, press *6 to ask them. Also, if you have something you want to send in the chat box. Okay, are there any questions? With this, we'll end then. Oh, wait, we have a question here. There's a question, can you give an example of how NorWeST database is being used in TMDL development? Dan?
Right. I think right now it's stimulating that discussion in that people can see that, and they've known this for a long time, that one temperature standard applied everywhere as a simple threshold doesn't make a lot of biological sense, because some streams are just naturally warmer than others. And I think the thing that we can do and are doing in NorWeST is making accurate maps of what the current thermal conditions are, relating those some of that natural variability and things that are associated with geomorphology, such that you can then start to go in and make context-specific regulatory standards that account for that, what that stream is just naturally. And so you could potentially fine-tune TMDL standards such that, in this particular stream, you get a much more precise estimate of what that local management effect is versus what the natural variability is. And I think that hasn't been captured formally and is reflected in the regulatory standards, but that's where the discussion is going, and what people are trying to figure out now how to do that we haven't been able to do in the past.
Thank you. We have another question. I noticed NLCD 2001 was used as an input data set. Will this be updated to the NLCD 2011 data set?
It could very well be. I'd have to go in and compare it to what we've been using. I mean, part of what our limitation is in doing NorWeST is that it's basically funded as a one-time effort through soft dollar grants. And so our big push is to just try to get through all the places within the original project area once. So we've got an organized database and set of temperature scenarios, and going back then and redoing things again gets to be problematic, just because the grant funding doesn't necessarily last that long. That said, having done it once, that takes care of 90% of the work that it would require to go back and redo it and update it with some additional covariates and add more temperature to some of these places where it's being collected. And so doing updates in the future would be a lot less time-consuming and expensive task than it was to do NorWeST the first time.
Thank you. If you want to ask a question, remember to press *6 so you can be heard. And we have one more question in the chat. It says, can you discuss the sustainability of just the data management infrastructure of the project?
That's another good question, and it kind of relates back to my answer to the last question, is that NorWeST is funded as a one-time effort through soft dollar grants. There has been some discussion about figuring out ways to maintain the database team such that as new data are being collected, that could be sent to a central place and people would look at it, organize it, and integrate it with the existing Oracle database and post the updated temperature data sets onto the website. But that hasn't become a tangible thing yet. I think if folks in the Pacific Northwest find the information that's being provided as being useful, that could be something that happens in the future. But as of right now, we're just doing it, and when we get done, we'll be done until people want to make that sort of ongoing data management thing happen.
Okay, thank you. Are there any more questions?
Yeah, can you hear me? I've got one question.
Yes, we can.
This is Mark Schnorris calling from the Pacific Climate Impacts Consortium, and I just wanted to thank Dan for a great presentation. But I guess we have doing sort of the same sort of work in BC is always something that we've sort of had on our work plan, but it keeps getting pushed back. And I guess one of my questions to you, Dan, is this must have taken some years to put all this together. And I guess what was your biggest challenge in sort of this entire project?
Well, I mean, that overwhelmingly has just been organizing that temperature data. If the temperature database, had existed when we started, NorWeST would have taken 1 year, not instead of the 4 years that it's taken. And so that is certainly the biggest consideration and would be part of the value of maintaining the database now that it's been built. And if you could just keep it updated, then it's not hard to update the temperature scenarios and spit out the most current information. The thing, though, that we had going for us in the lower 48 that is maybe a little bit different than British Columbia, though, is that we had a pretty good hydrology layer with a bunch of covariates already built down here. And so on the front end, the geotechnical aspects of figuring out how to make that layer work with the spatial network models, those weren't trivial tasks, but they weren't huge tasks either. And I think, I was just visiting with someone last night about, a proposal maybe to think about how you would do this north of the border. And I think the first step to doing that would be a sort of scoping proposal to get the geotechnical experts on the question and figure out exactly what the tasks are and how much time it would take to create the network you can then build all these subsystems on top of.
Yeah, in terms of your stream temperature data, I get the sense that you had the luxury of, you had a lot of time series data, and I know in British Columbia we have a lot of sites, but unfortunately a lot of it is just spot temperature data, and I'm not sure how that would work with the statistical model that you were using. Yeah,
I guess most of the temperature information we have is 1 or 2 summers of measurement at a site at most.
Right.
They do. I mean, there are the graph samples out there where someone puts a thermometer in a stream and they just record that one point in time. And we have had the luxury of having so much data that we basically do set a minimum criteria of that sensor has had to record temperature data for the full month of August before we'll use it. But there again, there's ways of use use what you can, because some data is better than no data, as long as you know its strengths and weaknesses. And then there's ways, even from a spot measurement, that you can know an awful lot about that stream's thermal regime, as long as you're treating it appropriately.
Okay, thank you.
Thank you. Are there any other questions? With no questions being heard, I want to thank everyone for joining, and thank you, Dan, for your presentation today.
Thank you, Mary. It's a great opportunity.
Thank you. All right, bye.